Hi everyone, today we're covering topic 9.8, Voltaic and Electrolytic cells. So as we move on to the second half of Unit 9, we're basically just going to talk about electrochemistry, which in essence is the chemistry of batteries. These are how batteries work, and they essentially work by redox reactions. So for the rest of this unit, we're going to be talking a lot about redox reactions, and so I suggest you go back and review some of those if you forgot some of the rules of redox reactions. We'll talk a little bit about it, but it is assumed that you at least know some of the rules. And so for the first few slides, I'm just going to define a few things. One is an electrochemical cell. And by cell, I don't mean like an animal cell. I mean like a cell where a reaction occurs. It's essentially like the battery. Your battery is your cell. And so it's a device that produces electricity or in other words, an electrical current, which is basically just moving electrons by spontaneous redox reactions. Now, there are two kinds of electrochemical cells. The first is called a voltaic, also known as a galvanic cell. These generate they generate power through a spontaneous redox reaction. And the second is an electrolytic cell. And these generate a current, and a current is basically just moving electrons through non-spontaneous redox reactions. In other words, you need an external power source. And so essentially you can think of electrochemical cells as an umbrella term. Both of these are electrochemical cells, and we have two types. We have a voltaic and an electrolytic. Voltaic is spontaneous, and electrolytic is non-spontaneous. Regardless, both of them are a redox reaction. A little bit more vocabulary that we're going to often use. The anode, this is the electrode where oxidation occurs. You can remember it by thinking about an ox, an equaling anode, ox meaning oxidation. And remember, this is a loss of electrons. And so at the anode, you lose electrons. You have the cathode, and this is where reduction occurs. You can remember this as red cat. And as a reminder, reduction means gain of electrons, and you can remember the mnemonic oil rig. Oxidation is loss, reduction is gain. So at the anode, you oxidize, at the cathode, you reduce. A little bit more vocabulary before I actually show you what this looks like in a real cell. You have a salt bridge, and this is a channel between the two different cells, these cells being the anode and the cathode, that allows for the transfer of ions. And so essentially, you'll have an anode, you'll have a cathode, and I'll show you this on the next slide, but between them, you have a salt bridge. Normally, this is something like KCl or like NaCl. That allows for those positive and negative ions to move around. You have a voltmeter, and this measures the voltage of a cell. Voltage is just, the flow of electrons. just the flow of electrons. It measures how those electrons flow and how much energy is in them. Reduction potential, which we call E, this is a measure of how strongly the electrons are attracted to an ion, which we call V. And then again, oxidation means losing electrons, reduction means gaining electrons. Oil, rig. Okay, so this is what an electrochemical cell looks like. Here at the top, we have our voltmeter. This is what measures our flow of electrons. On our left, we have our anode, which is where oxidation occurs. In this case, our oxidizer is zinc. Because it's oxidation, it is losing electrons. So we have zinc 0, right? It's just the solid, has no charge. That forms zinc 2+, and 2 electrons. In an electrochemical cell like this, you'll normally have the metal, right? So this is just solid zinc, which is what this metal is. And it'll be in a solution of ions. And so in here, I have zinc 2+. And this reaction is occurring, this oxidation. As this oxidation is occurring, you can see it makes electrons. Those electrons travel up the wire through the voltmeter, and that is how you measure the electrical current. Right? You measure the flow of those electrons. It goes from the anode, from the negative, to the cathode, where the reduction occurs. Here, our cathode is copper, and so we have this solid copper rod in a solution of copper 2+. So since the reduction is happening at the cathode, the reaction here is that we have copper 2+ plus 2 electrons makes solid copper, which makes sense. The electrons are flowing from the anode over to the cathode and then causing this reaction to happen. Now, this flow of electricity is what actually generates the electricity in a battery. So in a battery, you have both an anode and a cathode, and this reaction happens, which then generates an electrical current, which you can use to power things. The problem is, what you might notice here, is because the electrons are flowing in this direction, this cell is becoming more positive, and this cell is becoming more negative. And eventually, we'll have so much positive and negative that the reactions will stop. And that's what this salt bridge is for. We have KCl. Because this side is becoming more positive, we have Cl minus coming down from the salt bridge into solution, which balances everything. And equally, we have K plus coming down into the cathode solution in order to balance everything. I know this is a really messy slide, but in general, at the anode, we have this reaction happening. At the cathode, we have this reaction happening. Plus 2 electrons. That'll make solid copper. And as a result, what's happening here is that the electrons go from the anode to the cathode through the voltmeter, and the salt bridge will give Cl minus to the anode solution and K plus to the cathode solution. Something else that you can measure here, of course, is the reduction potential. And you basically do this with a table of standard reduction potentials for each of these reactions. Normally you would be given this on a problem, and there are also tables available for these that'll be on the topics page. But each reaction has its own reduction potential. For copper 2 plus, reacting with 2 electrons to make copper 0, this has a reduction potential of 0.34 volts. For zinc, this electrical potential is negative 0.76 volts. And so now if we want to find the reduction potential of the entire cell, E of the cell, is just equal to the reduction potential of the cathode minus the reduction potential of the anode, which is 0.34 volts minus negative 0.76 volts, which is equal to 1.10 volts. Now notice, right, in our cell, for our cathode here, this number is positive because that's actually what's happening. We're actually reducing it, and so that's what's happening at the cathode. For the anode, this is actually the reverse reaction, because what's actually happening is we're actually oxidizing it. And so if you flip it, we also have to apply a negative symbol there, which is why we eventually end up with this positive value. So let's look at another little example here of how we can draw up an electrochemical cell or understand how an electrochemical cell will work for this silver and copper cell. And so first we would just look up the reduction potentials in a table. We can see that the reduction of silver, Ag plus an electron to make Ag solid, has this reduction potential of 0.8. For copper, we just saw its reduction potential is 0.34. In order to figure out the anode and the cathode, the higher potential is always reduced. In this case, that's silver, and so this is reduced. So this is our cathode. This one is smaller, so it's oxidized, and this is our anode. So here, Ag is reduced, Cu is oxidized. If we want to find the electric potential of the cell, again, that is E of the cathode minus E of the anode, which is 0.80 volts minus 0.34 volts, which is 0.46 volts for the entire cell. The second step is to write the half reactions and then the overall reaction and, of course, balance them. And so first we should look at our reduction. That's where our silver is, and so we have Ag plus an electron makes Ag solid, and then we have our oxidation. Where we have copper solid reacts to form copper 2+, and it will let go of 2 electrons. Of course, we have to balance these, and we can see here we have 2 electrons in 1, so we should multiply this entire thing by 2. So we have 2 Ag plus 2 electrons makes 2 Ag solid. And then we just add up these 2 reactions together. We end up with 2 Ag plus copper solid. The electrons, of course, should always cancel out. We make 2 Ag solid and copper 2+. That is our overall reaction that's happening in our electrochemical cell. And of course, the ions should be aqueous. And then here's what's actually happening. At our anode, we have what's being oxidized. In this case, that's the copper. It's in a solution of copper 2+. The electrons go from the copper through the voltmeter, and like we calculated, that potential for the entire cell is 0.460 volts. Those electrons then travel over to our cathode, which is silver. This solution will produce copper 2+, and the Ag2+ in solution will go towards that metal. And of course, our salt bridge will send negative ions, in this case NO3, into the anode, and positive K plus, into our cathode. And essentially, this is how your electrolytic cell will look. And so when we're trying to think about how to design a cell like this, we should follow those steps. First, determine anode and cathode. Second, determine the reduction potential of the whole cell. 3, balance the half reactions. Four, write the overall reaction. And then 5, draw the electrochemical cell. This was kind of an introduction to explain how these work. As we go throughout the rest of the unit, as well as in class, we'll go over some problems to see what this actually looks like together. For now, that's all. Thanks, guys.